So welcome. Today we are in part one of our data calculations in ARM. Previously, we kind of did all of this in one session, but this time around, we're going to try to break things up a little bit, spend a little more time on each example. So today, we're focusing around the items that are on our transform dialog. So we'll be looking at some calculations you can do with subsample data, talking about control corrections like Abbott's, and then also kind of our general calculation creator called user formulas. And we'll look at, kind of the real basics of that, and hopefully we'll have time to dive into even some more advanced functions you can do with the user formulas. And formatting wise, we'll be going kind of back and forth between this presentation and ARM. So I try to kind of summarize our available options, and then we'll dive into ARM and actually work through some examples so we can see the calculation in action per se. So our first one here off the bat is subsamples. So assuming you are taking some sort of data that's got multiple values for each plot, there's a few different calculations that we can do with data like that, primarily to summarize and give us one value per plot based on all of those subsamples you took. A common reason for subsampling to begin with is maybe the rating or the observation you're taking is inherently very variable. Something like maybe presence of insects. You could have one plant that has a bunch and several that don't have any. And so if you were only limiting yourself to one small sample of a larger plot, you could be really overlooking something significant. So maybe we need to go out and survey 10 plants, or a quarter area of our entire plot, or whatever. And you do that repeatedly. We want to try to understand, then learn a little bit, do some calculations based on what we've collected. And in ARM, we have a couple of different ones. So the first one, super basic, the idea of just summarizing these down to a value. You can just simply average those subsample values. And what will happen is in ARM, you'll have the column. Actually, let me just go to ARM quick so we can visualize those subsamples. So I've got this assessment here with 5 subsamples. So for every plot, I've got 5 different values that we took. And what we can do then is simply create a new assessment column based on this data that I've taken to give ourselves a calculation, a calculated number. So something as simple as creating an average or doing a sum, depending on the type of data. If it's more about harvesting, you might want to sum those subsamples to get the grand total from that plot, or if it's more of wanting to get the average response from that plot. So we have these here are action codes. So just about everything that we're going to be working on, both this session and the next one, most everything ends up coming back to an ARM action code that creates, really provides instructions to ARM. We saw that a little bit when we were doing our data review in the assessment header, where we're describing the columns, the assessments that we're creating. There is a row called the ARM action codes. And so these are all instructions, and we can see that in some of these columns here, we will be defining an action that tells ARM how to calculate the values that we see on the screen. So I've got in italics, these are calculated numbers. I did not enter them. They're not ratings that I recorded, but instead they are calculations based on the raw data here in column 3. So back to the PowerPoint here, the action codes, TAS or TSS, will give us the average or the sum of our subsamples. A note here, you certainly can create a brand new column that will give you that value. Don't know how often that would be entirely necessary to simply create the average of those subsamples if you're only wanting that in order to perform ANOVA or some analysis or graphing. Wouldn't really necessarily have to create an entirely separate column with those numbers, because ARM, when doing analysis, when doing the ANOVA or graphing or things like that, kind of the default action for subsample data is to first create first calculate a plot average. So our ANOVA, the fiscal analysis that we have, doesn't go as far down to the subsample level. We'll always calculate a plot average first and then just use the plot averages for the analysis. So really don't need necessarily to have to create a separate column for every subsample rating if we're only using them for the analysis. So the default would be average in that case. I do want to show if your data you want to sum, and the sum of all of those values is really what you would want to use in the analysis. I'll go back to ARM here. You can use sum sub. I'll just bring up that action code here to show that this is a designation for the data that you're taking to tell ARM, I'm not interested in the plot average for this type of data. I actually want to sum all of the subsamples together, and that total of the subsample values, that's really what I want to summarize. So this passes those instructions to ARM, so it knows that for this data, here I was counting out how much fruit we got from each of the plants in our plot. And so that total amount is really what I'm interested in summarizing. And so by putting in this sum sub, something like plot 102 here, I've got 1, 2, 3, 4, 5. 15 would be my total instead of an average of just 3. And you can see actually if I click away, even the display in ARM will change to use that sum. So it shows that 15 instead. So that's how you can control the default behavior with subsamples and the analysis. If I want an average, I don't have to do anything special, but if the subsamples should be added together, sum sub will work there. A couple of other calculations that we can do with subsamples. Instead of necessarily having to type in your action code, we do have an interface for that. I typically recommend just clicking in the column that you want to summarize, and under the Tools menu, we have a command to transform. And this is where we'll go to generate most all of these calculations, these formulas that we have today. So we have a nice list of a bunch of different transformations that we have available built into ARM. The first 3 are kind of tied into data correction transformations. We covered those in length with our data review session a few weeks back. Not super applicable outside of that. really just trying to address the assumptions of ANOVA. This next section, however, are related to subsamples. So we talked about the average and the sum, and all we would do is select one of these options here. If that's what we want to perform, down at the bottom, we can make sure to put which column number we want to convert. And because we were already clicked into column number 3 here, when we selected transform, that's what gets filled in here. Then we can choose what column to put the new data in that we're going to create from this transformation. And ARM will usually default to whatever the next empty column is. I don't know if it'll let me scroll here. No, probably not. So it looks like I've got 29 columns right now. So it'll just make a new one all the way to the right. So column number 30 would be this new calculation that I have. And if I want, I can specify how many decimals of accuracy I want to display for this new transformation. So couple more subsample options. We do have a percent incidence calculation. So based on all of the subsample values in a plot, we can calculate the percent incidence of how many of those subsample values are not 0. Or if you're doing maybe a rating scale, so the idea of 0, no response, is actually the numerical number 1, then you can also choose this calculation. It's percent incidence, but instead of looking at 0 or not, it looks at the number 1 or not. And that's actually what I've done in column number 4. So I'm just going to repeat as if we didn't have column 4 already. It'll yell at us probably that will overwrite, but that'll be fine. It'll give us the same thing. So I want to do a percent incidence where 0 is none. So we'll get a percent of what percent of my subsamples in each plot, what percent of them are not 0, had some sort of response to them. So I'm going to calculate, I'm going to base that on column 3. I'm going to store this data into column 4. And we're doing the percent. I probably don't even need any decimals of accuracy. Like I said, ARM is going to be a little concerned because I chose column 4 that already has data in it. So I'm going to say yes, because I know I'm just repeating the same calculation. So here in column 4, I've got a test incidence percent here. We can see the action code is kind of what ARM knows, how ARM knows what to calculate. I don't really need to memorize that code necessarily because I can just use tools transform. But for if you do kind of like to know what's going on behind the scenes, that's the instructions, how ARM knows what to do here. And like I showed, you can see that the numbers are in italics. That's trying to show that these are calculated values. And we have that designation in the header as well, where it says it's calculated. Also, when I'm clicked into this column, you can see that column number 3, the box is outlined in blue. And that's just a visual indicator. We calculated this value in column 4 based on column number 3. So just trying to help kind of understand how these things are related. And so my incidence here, if we look at plot 102, I have 2 values that are not 0. So 2 out of the 5 gives us 40%. That's our incidence calculation. So this can be nice instead of having to, as you're doing the rating, trying to keep track of the incidence as well, you can just simply jot down your raw data, knowing that in ARM you can get that calculation. So you don't have to keep track and jot down another column of incidence I'll just take the raw data and have ARM calculate it for me later. So that's our incidence calculation. Again, just depends on what is no response. Is it a 0 or a 1? You can choose which one of those options. Then the last subsample value calculation. This one is not on the transform dialog, but it is in our action codes list. And it allows us to count how many values are within a certain range. So it'll be this transform in, if you will. That would be the code here. And then we tell ARM a couple pieces of information, what column number we want to use as our basis, and then the lower bound and the upper bound of values that we care about. A lot of times we might actually see this idea surface later as kind of part of a more complicated calculation that you might want to do. But I kind of like showing this as its own entity, just to kind of get that visualization of what it is we're doing. So I have that here in column number 5. You can see this TIN action code. We're counting subsamples within the plot. How many subsample values fall between the range, the two numbers that we're specifying. And in my case here, we care about anything that's between 50 and 100. So maybe the idea is that we've got our rating, and then we want to kind of categorize. Really anything that's 50% or higher is what we would consider extreme or not marketable, or whatever significance that holds. We can kind of encapsulate that down to give us an indication of, in this case, maybe the severity of how bad things are in that plot. So what we're looking at is how many values in that plot are between 50 and 100. And of course, these first few plots are all 0. Nothing is... There we go. We've got one that's somewhat interesting. So I've got 180. The rest of these are less than 50. And so of those 5, there is 1 value that is in our range. And here we've got 3. So it looks like this plot 202 is really struggling. Yep, there's 3 of them that are 50 or higher. So again, maybe this column itself isn't super summarizable, but it might be the basis for some other calculations we might end up wanting to do. So that's just one more function at our disposal for subsamples. Got a question here, maybe an idea. So would be possible to have boxes to have the calculated data going directly into the first empty column, or a column number that you would indicate, but creating a new column. Oh, sure. So I think the idea, looking at our transform dialog, wanting to, let's just say we're creating something from 3, and certainly the default here has been just to add 1 to the end. But I think you're suggesting, boy, it'd be nice if we could like insert. So maybe I want to insert a new column right at column 4 with my new data. I think if I'm understanding that correctly, it definitely seems like a good idea. We have a command to insert a new column that you could do, and then after inserting a new column, you could do tools transform, sure it would be nice to tie that sequence together into one option. So I'm just going to jot that down here to pass along to our developers as a good feature request. I'll just call it insert new column idea for the transform dialog. Just to show the one way to do it currently that requires several steps would be to first, right click and insert a data column. And so you could put in an empty column and then perform your transformation. But I agree. I like your idea of having that all in one go. Okay. So that's about it for subsamples. Our next category here for common calculations that you can do in ARM is the idea of control corrections. So the basic setup, of course, assumes you have a study where you have an untreated check or your control treatment. So I'm gonna have some plots out in my field where I do nothing to them and want to compare, the response for the treatments of interest. How does that response compare to having done nothing? And that can be really useful to understand the responses we're seeing in our trial. So typically you would take a rating, of course, on all of the plots for this key piece of information we want to know, and it is more beneficial maybe for us to understand that the responses we get, how do those compare specifically to the response we saw in the check or in the control plots. So we have a couple different ways to do this. The first one here is really trying to calculate efficacy relative to our check. So the idea of that is the percent reduction that our treatment had relative to the check. So the most common one, most common calculation, at least that we hear, that people refer to this as, is the Abbott's calculation, which originally formulated for infestation assessments on a uniform population. But I think mathematically and philosophically, these ideas would apply to lots of other kinds of research as well. I think the key would be you're looking for that reduction. How good did our treatment do? The check itself, the calculation is going to be 0 for the check. So the check, we did nothing, and so nothing was done. What did our treatment accomplish as a percent of that? If we did nothing, that's our baseline. Did we control everything? If we got a response of 0, there were absolutely no pests in that plot, we would say we controlled everything. We had 100% efficacy in that plot. And then everything kind of relative to that. So there's a few different ways to calculate this. The baseline, the regular, I want an Abbott's. What you would do is, well, actually, let me go into ARM before we talk about the different action codes. Let's do the regular Abbott's, if you will. So here I've got my pest severity rating that I've taken, and now I want to calculate. So we'll go to transform. I want to calculate my Abbott, the percent of untreated. So same thing as last time. We'll kind of cheat just to see. I'm going to store this in column 2, even though I've already done that calculation. Actually, let me put a couple, oops, I didn't want to cancel all the way out. We want to do the Abbott on column 1, put it in column 2, and just to limit how many digits, we'll put number of decimals down to 2. Yes, we'll just repeat that, copy over that. So now I have my Abbott's calculation. Key difference here is our rating unit is % of untreated check. And the action code that triggers this calculation is TAB, transform of Abbott's. And so what we are doing here is calculating relative to the check. So just taking plot 104, for example, our response was simply a 1.3. And we take that relative to our check response to see that we got a 74%. So of doing nothing, we're down to a 1.3. So we reduce the response by 74%. If we look at that next plot, it's even a smaller response. So we have controlled even more. So we have an 80% control. So that's the idea of our Abbotts here. The higher calculation is showing we have done better. We had higher efficacy relative to doing nothing, relative to our check. Now there are a couple other ways that really what numbers are we using to get this % reduction. So there's a couple of different types of Abbotts, I guess we'll say. And I've tried to summarize them here in the table to kind of make sense of the options here. So our regular Abbotts that we chose right off the transform dialog, what we're doing is calculating our response relative to just the one check value that's in our same replicate. And that is perfectly reasonable to do if the check is pretty consistent. So if I go back to ARM, we can see in this case, our check response was reasonable. They're all pretty similar. We didn't have crazy variation in the check, so we feel pretty fine to do that. And so specifically, when we're looking at this calculating plot 104, we're comparing this 1.3 specifically to just plot 102. So we're looking up in replicate 1, what was the response from the check? That was a 5. And then we'll calculate 1.3 is what % of 5 to get that 74% reduction. We reduced ourselves from 5 all the way down to 1.3. That's our Abbott's calculation. However, if we don't quite have that consistency, where there's a lot of variability in the check, then we really are setting ourselves up for some trouble with our calculation. We're going to have a lot of variation in our efficacy calculation as well if we're using each individual value. Because of course, if the response in replicate 1 was really extreme, if it was an 8, well, now all of our calculations are going to be, maybe skewed a bit. So if we don't really feel that we have a good, let me undo that so our calculations don't change. We don't feel like we had a real good consistency in our control, and we don't want to open ourselves up to all that variability in our calculation as well, then we can use the UTAB transformation instead. So it's the same idea of calculating efficacy, but instead of using the check only in the same replicate, we're going to average the check. across all the replicates and use that as our basis for calculating our efficacy. So, oops. Still calculating, a different value for each plot, but it's really just that basis of that check value. What are we comparing to? Well, we've got a lot of variation, so let's try to smooth that out a little bit as we're calculating our efficacy. So this one here, the U tab, sorry, I'm switching back and forth a lot, is not on the transform dialog. So we have just Abbott here. That's the regular TAB that you can use. But if you decide to go with one of those other options, you'll find that in the ARM action codes list. So instead of doing Abbott, I could convert this if I wanted to. And it would be U tab. So I might just filter that action codes. I just typed in tab because I know all the different variants are all contain that code. So I have at U tab, which is our Abbott per plot from the mean of untreated treatment. So if I select that one, ARM is then going to ask, okay, we're going to do this calculation. What column do we want to base that on? And in my case, I think it was column 1. Yep. And I wonder if it just created a new one entirely instead. So I'll just hand type. Same difference. If you select from that list, you could see ARM was kind of trying to give an interface, but you can also just hand type the code. I know it's at U tab, and then instead of that N, I put in the column number. And there we can see now that our calculations changed a bit. So now we're going relative to the mean of the check. And then the same idea again, if we really have a lot of variation across the whole trial, we just really aren't satisfied with how consistent even the treatment response was across replicates. You could even go one step further and take the treatment mean relative to the check mean. So instead of each individual replicate getting a calculation, we're really only calculating one value per treatment. So that would be T-tab. So we'll go back here one more time and just convert this to T-tab. And you'll notice then with that calculation, we really have the exact same value for every replicate within a treatment. So if we run this through the ANOVA, we actually won't get any analysis at all because there's no variation. So sometimes we could ask ourselves, well, if that's the case, do I really need this column because I can't run statistics on this? It's really just this value, this 57.7 is all that really matters to me. We don't need to see we can't see significance from it. It just informs us of that. So that's our final note, is there is an action code that you can put in your original column, this APC. It's going to perform that percent control and just put it on our AOV report. So I'm going to real quick bring up the ANOVA report here. And actually, since this is column 1, we can probably see it right here on the preview. Yep. I'll zoom in even a little more. So column 1 was that our raw data of our assessment. and we have our treatment means, our mean comparison letter, all like we would expect for that data. But because we use the APC action code, we get one more piece of information. Here underneath the treatment mean in the parentheses is that Abbott's percent. Again, no statistics can be run, and we can compare that to right here on the right, where if we were to put that T tab as a standalone column, we really get the same information. In fact, ARM reports this a little nicer because it does report it as a percent, which it is, and we don't have to mess with all of this. Well, there's no statistics. Can't do statistics on those values because there's no variability. There's just one value for each treatment, as if we only had one replicate or something. So no stats can be run, so maybe you just want to put it on your report as that percent to reference. That can be valuable too. Or maybe you want to do both. I would say the one other difference, if you do the APC, these values aren't in the trial in that sense. You know, they're not in the trial file, they're only visible on the report. So, you know, if your company has like an ATD database, having a separate column is advantageous because then these numbers are exported into the database. So then, you know, another reporting tool or summarization could utilize those calculations, as opposed to if you only use APC, then those values really only exist on the report. So might work for some groups, maybe not others. So those are the different Abbott's calculation to really calculate efficacy. Couple other ways to calculate efficacy. There are a couple of other calculations for different types of research. First one here is Henderson-Tilton. Most commonly infestation rating for a non-uniform population. And the key, especially with that one, is when you're adjusting for a pre-treatment assessment. So you go out and take an assessment before any applications are made. And that kind of is your basis. Then after the treatment's been done, then we'll go out again and take an assessment, and then we can do a before and after calculation. So that is Henderson-Tilton, and then Schneider-Orrelli, that is for mortality ratings. Don't think I have either of those in this trial, but just to point out, they are here on Tools Transform. So there's the Schneider-Orrelli and the Henderson-Tilton. And ARM will prompt you. So for like the Henderson-Tilton, now there's actually two boxes. So it's asking for which assessment was your pre-application before the treatment was applied, put in that column number, and then the second column number is the data after the applications were made. So there's two different data columns there that go into this calculation. All right. One more category of control corrections. It's really just kind of the inverse calculation, if you will, for relative to your check. And this one would be when you want to do a percent of untreated. You're really wanting to gauge the performance of your product relative to the check. So think of that as really when you have an assessment that's a positive effect, something like your yield or your emergence. The check is still your baseline, and that would be 100% as your baseline performance, if you will. And then you're calculating what happened with the treatment. Did Did the treatment exceed what the check did? Is it 110%, 115%? Or did it do worse? Did it come in at only 90%? So we actually saw reduced performance. So very similar ideas in calculations to the Abbotts. Got a table here because we're doing the same idea as far as a couple of different ways you can calculate this relative calculation. So we'll call it the regular one that is very similar to what we did with Abbott's is the transform UPOC, so percent of check transformation. So we are calculating, once again, we'll take the value in plot 101 and calculate the percentage relative to the check in the same replicate number 1. So again, if we can assume the check is reasonably consistent, that gives us a reasonable response then and calculation. However, if we're really worried about variability, we really don't have the middle option in this case for the percent of untreated. We kind of skip to the end where you would take the mean of your treatment versus the mean of the check. And that would be the TUPOC. So exact same idea as with the Abbotts, but we're just getting the percent of the value instead of seeing the efficacy. And I've got an example tied to our yield in this case. Got the whole sequence of calculations, but here in the end, we've got our tons per hectare yield result, and then I perform a percent of check. So you can see then the check comes in at 100, and then how much better did we do? Well, hopefully it's better, hopefully it's not worse, is our calculation here. And we have the UPOC, UPOC. The R on the end of this just means use the column directly before this one instead of giving a specific column number. But and I won't show this, but the exact same idea with that APC. We have the same idea where you can get these percentages just on your report instead of making an entirely separate column. We just use the APOC action code. All right. That one's a mouthful, trying to get the right terminology for pretty similar idea, but also entirely different calculations, entirely different situations you've used them in. But hopefully that helps separate those different options for calculating relative to your check. All right, last option here, our third subject, I guess I should say, is user formulas. So this is, I would say, comparing to Excel, essentially. When you're in Excel, if you've typed in your data, then you just go to the very next cell and then start punching in some formula. Let's have Excel create some calculation for us. That's really what we have available to us in ARM as well. It's a little more formal. We kind of have to follow a specific process because we have this structure in our columns, so we can't just throw calculations everywhere. But the idea still applies, where we really have an open box here to fill in all sorts of different types of formulas that we might want to make. So let's first just do that here in ARM. got my data that I want to transform. And just like we had before, the command is tools transform. But instead of these built-in functions, I can use this user formula. So as soon as I click on that option here for user formula, we actually kind of expand this little panel to bring focus to the fact that I have this open box to type in a formula. So there's some help guidance here right above to kind of give us an idea of what we're supposed to do. If you want to know kind of the full list, there are some formula templates. So it tells us if I press the F9 on my keyboard, there's a couple of formula templates. I don't know how many of these are super useful to just click on and use, but really would be helpful to let us see what types of things are possible. We'll kind of step through some of these capabilities, but it tells us what we're trying to do here in the description, and then shows you how to achieve it, what you would actually type into the box. The other real helpful thing, if we click on the help button on this dialog, see if I can get help to load. As with pretty much every screen in ARM, that help button just runs through every option toggle on the screen that we're at. It'll tell us what we can do. So you can see all the different transformations. We talked about a few of them. But the very bottom of this table is the user formula. And so I click on this link. I go here a lot because it's helpful, because we've got all the different things we can do in this box, different functions, different techniques and things. So if we run short on time, you can find even more items here on this help topic. All right, back to the PowerPoint. Kind of the real basic rules of formulating a calculation here. First and foremost, trying to use data that you have in ARM, you would reference the data column with a bracket. So for example, this here would take the data in column 1, add it to the data in column 2, and give us a third column that each plot just has the sum of what was in 1 and what was in 2. That would be our calculation. We saw the F1 help for all the different functions and things like that. So let's go here. Once you create a formula, that's what I've done here. I've created 2 different formulas related to column 18. Once you do that, ARM puts in the action code, just a very generic T1. That is the first transformation that I have created in this particular trial. If I want to know what that transformation is, I've received this, the trialist must have created this, and I'm not exactly sure what was done. If I'm clicked into this calculated column, I can go to Tools Transform, and ARM will show me in this box what T1 is. So T1 is column 18 multiplied by 2. And sure enough, we can see, oh yeah, wasn't particularly fancy or sophisticated equation. That's what we ended up getting is the response on 18 just doubled. I can do the same thing for column 29. What is this T4? And the number itself, as we can see, doesn't really matter. We've skipped a couple, but really doesn't matter. ARM is just keeping track for us. This next calculation uses a function. So we have at sum. So just like functions in Excel, it can do a little more sophisticated calculations without us having to explicitly write it all out. Now this one isn't super fancy. We could have handled it ourselves, but at sum is going to obviously sum up all of the columns that we define within the parentheses. So I've got everything between column 18 and column 19. So it's just really those two columns. We can sum them up into this third column. And you can see the basic math of how that's coming up. So that's the basics of the column, the column transformation. Let's go back to our slideshow here. There are more sophisticated things you can do. A common one would be wanting to use your untreated check, for example, within a calculation. So kind of like recreating that Abbott's that we were just talking about. You can do so manually with your own calculation. So this example here, you'll notice, we refer to columns with brackets. You can put in the C next to the number. It's just easier to mentally think that's column 1. ARM treats it the exact same as if you just put a 1. Same exact thing, but might be easier to identify, and especially useful in this case, because now I can say, take the data in column 1, the value there in column 1, and divide it by the value in column 1, specifically the untreated check. So using this TU is the special code so ARM knows, look up your untreated check. I go back one slide, we had that screenshot there. What is the untreated treatment number? Look that value up and use it here. So here, I'm doing a percentage calculation there. So you have the ability to dig further into a column to use different pieces. So question here, looking back at that T4, for example, I've got a T1 and a T4. Hey, what happened to treat to 2 and 3? Number 1, we can see here, if I drop down this list, I can actually see the 4 that I've created. As you said, if you delete a column, if I create this T4 and then later I don't want it, maybe I make a new column with the right calculation I want, and I just delete column 29. Because yeah, that wasn't what I wanted, it didn't work out. Logically, the next one will be T5, and that T4 then would disappear. Actually, let's just do that real quick, because that might be more useful. Let's do tools transform. Let's just take column 18 and let's triple it instead of double it. Do real exciting things. And put it into column 30. Awesome. This is what I really need. So then I delete column 29. Yes, it has data, but nope, I don't need it. Now, if I go back to our formula, as we said, now we've lost that T4. It doesn't really exist anymore because we got rid of the column that that we had there. What'll happen, you can kind of clear that up actually when you press save. We should see a prompt. Here we go. So after it's saved, ARM has noticed, hey, we've got 5 transformations, but we're actually only using 4 of them. So there's a question here, do you want to delete the transformations that are no longer referenced in any column? So the warning is, hey, if you do this, we might renumber them. Again, we really don't care that this is T5 versus T4, but that's exactly what will happen. So if I don't really like that, I kind of like those numbers all to be the same, so I know how many I've really used, then I would select yes. And this is going to delete that old T4 that we aren't using anymore. And if I know I don't ever want it to use it, I can delete it by saying yes. And now you can see T5 is now T4. It's gone. We've renumbered. Everything's nice and neat. Great question there. And it is a kind of a common question, that dialogue. It's not super clear what's happening. Real quick, want to show some of the advanced user formula functions. We're close to time. I won't be able to cover all of them. I'll kind of put a pin in this, and if we've got time next week, maybe we'll be able to cover a couple of these in a little more detail. But there really is a lot you can do with these formulas. I've been very, very boring with my examples, but it does have a lot of capabilities to be able to create fairly sophisticated calculations. The one I like to show especially is you can utilize a piece of information that's in your assessment header. So something like sample size, maybe, you can actually utilize in your calculation. And it's kind of self-referential to be able to extract an important piece of information, something like your sample size, maybe because you want to standardize. So I can set up a calculation, and it doesn't matter for each given trial. I send this out to 5 trialists, and they maybe have the ability to choose their sample size, whether they look at 5 plants. Sometimes they'll do 10. Some of them will do 20 for whatever reason. They can choose the sample size based on how variable the trial is going. I can utilize that value in my calculation so that I have a standard column that'll be real useful in my multi-trial analysis. And I'll just show that real quick, that I could, if I wanted to standardize this column here for the 5 sample size, what I would be doing in my transformation is maybe I want to take the response from column 18 and then divide it by that sample size value. First, I need to reference the column number. So in column 18, I want to pull the header information so that I have the letter H to say reference in the header. I want this field. And so you need to look up the field ID code, which I'll show in a moment. But for the sample size, I believe it's EBS. So this is going to take the value in column 18 and divide it by that sample size in that column. And if I did that right, 10 divided by 5 is 2, 5 divided by 5 is 1. So it looks like I did that right. Now the key to make that work is looking up the field ID code. So if you click into the field that you want to know what is the little code, and that code is just the way ARM knows what are you talking about, what box are you talking about. If you hold down the Alt key and then press F1, that will bring up this little box that is technical details on this specific field. And really about the only thing we care about is that field ID code. And that is EBS. So it's usually three letters or symbols or something like that that will be the code there. And that's how you can roll that into a transformation. So one more time, to see that box, you click in the box, you hold down the Alt key, and then F1. And that's how you can see the code. If you need any help with the calculation, or just want to know, hey, is this even possible to make this an ARM? Feel free to contact us. I'm kind of a numbers nerd. I like digging in transformations and figuring out what levers we can pull to make calculations. So more than willing to help kind of put the right logic together, or let you know even if it is possible to make a calculation. All right, well, we've kind of run ourselves out of time. Like I said, if we get time next week after some of our other topics, we might be able to loop back to a couple more advanced formulas, but the biggest thing on that is just to know it's there. One more time, that tools transform. You just have an open box to make whatever you might want to make for a calculation in ARM, which then unlocks the ability to analyze that data, that calculation that you have. All right, so thanks everybody for joining, and hopefully maybe we'll catch you next week when we move on to a few other transformations and calculations we can do. Well, thanks everyone.